All right, we're going to look at the next section of Module 6, which is actually the last section we're going to cover today. It's on symmetry, and we're going to look at different types of symmetry, whether it be line symmetry or rotational symmetry. And this fits in with what we're doing right now because it does kind of deal with the concept of rigid motion. You know, the symmetry is for an image that's locked into its position, and we're just going to look at the different ways we can find symmetry. Okay, so symmetry defined is a figure has symmetry if there's rigid motion. And what we're looking for is, in this case, line symmetry that will map a figure right back onto itself. So line symmetry, or reflectional symmetry as it's called, is when you can draw a line in a figure, and it folded along that line, the two halves match up perfectly. All right. If you set a mirror on it, it completes the image on the other side, is another way to look at it. All right. So as I said, if a line has, excuse me, if a figure has line symmetry, then it can be mapped onto itself by a reflection in a line. All right, here's an example. If this was one figure, if the green and the blue or whatever color that is, if it was all one figure and I drew that line of symmetry, that dashed line, if I was to fold it on that line, the two halves would meet perfectly. They'd set right on top of each other. Okay, so that's the idea of this, of line symmetry, and you've done this before. So in this case, they're asking us what lines of symmetry are available in this shape. Now, it does take special shapes to have lines of symmetry. In this case, you have a rectangle. So you got four right angles, opposite sides are the same length, and that lends itself to having symmetry. We could have a vertical line drawn here that if we folded on the vertical line, we would match the two other parts up, or the two halves perfectly. We could have vertical line, or excuse me, horizontal line symmetry here, where if we fold along that dashed line, we would fold the shape right onto itself. So there's two lines of symmetry there. Now, this next image is a triangle, and if you look at it, it's what we call scalene, which means all three sides are different lengths. It's going to be difficult to have any kind of symmetry here because you need two sides to match up to be able to fold it onto itself, so to speak. So this one's not going to have any symmetry. And then our last example is a hexagon. It's got six different sides, and this is a regular hexagon. All six sides are the same length. All six interior angles have the same measure. And because of that, we do have several lines of symmetry. Now, if I draw them all in here, you got two different types. One type that kind of bisects the sides, and then a second type that bisects the angles. If you fold it on those lines, it folds right on top of itself. So there's two, three, four, five, six different lines of symmetry that you could have in that image. So that's what we're doing here, identifying lines of symmetry. How, what lines could I draw inside the shape so it would fold onto itself? Okay. And then we have rotational symmetry, the other concept. And what we're talking here is, this is kind of like when I showed you rotation before, how we stuck a pin in the origin and rotated the actual coordinate plane. Well, now we're not rotating the coordinate plane. We're actually going to stick a pin inside the shape and just rotate the shape. And then how many times during a 360-degree rotation does that shape get rotated right on top of itself so you can't tell it's been moved? Um, the point in which the figure is rotated onto itself is called the center of symmetry. So that pin placement is stuck inside the shape. That's the center of the symmetry there. In this case, if you look at this shape, this looks like a green square to me. All right, and then you can see that point in the center. If I was to stick a pin in that point, and then this shape was able to be spun around, there's actually three different stops we could make before we got to 360 that would map that image right onto itself. So if I did a 90-degree turn, a 180 turn, and then a 270-degree turn, that would put that image right on back, right on top of itself again. All right, so those are the different rotational symmetry that's available there. The order of symmetry is the number of times it's rotated on its way through this 360. So in that drawing that I give you here, and this one up here, this let me get my mouse over here. Okay, in this one, that has an order of four because a 90-degree turn, a 180, a 270, and back to 360, it's back into itself again. So that would have an order of four. The magnitude, what they're asking is, what's the smallest degree rotation you can make before that shape is right on top of itself again? And what we do here is we're going to take 360, which is the full rotation, and divided by the order, which is the number of times it rotates onto itself. And in our case up here, if I take 360 and divide it by 4, I get 90. So this shape has a 90-degree of magnitude. In other words, every 90-degree turn, it's right back onto itself again. Okay. Point symmetry, really just talked about that. It's when you choose a point that you can rotate the figure right on back onto itself, and that's the point of symmetry. Okay. These are typical questions you're going to get tonight, going back to some of our rotational symmetry from the last page. This says state the order and the magnitude of symmetry, identify the point of symmetry. In other words, that point of rotation that we're using. So this first one is a pentagon, and it's a regular pentagon, which means all the sides are the same length, all the interior angles have the same measure. And they're saying, number one, is there rotational symmetry? Well, because it's regular, like I just said, yes, there's rotational symmetry. What is the order? How many times could you turn that? Or I should say, how many times during a 360-degree rotation is that image just like it looks right now? And the answer is there's 5. Then the magnitude is going to be 360 divided by 5, and it's going to be 72. So every 72-degree turn about this point in the center, that's our center of rotation or point of symmetry here, every 72 degrees makes that image look just like it looks right now. Okay. The next one is, does it have rotational symmetry? And if you're looking at it, you can see that two of the angles, these two angles down here are 90 degrees. These angles are not 90. So if I pick a point, again, we're going to rotate it around a point in the center of this somehow. Am I ever really going to be able to turn it and make it look like it does right now? And the answer is no. Okay, so there's no order, there's no magnitude because there's no rotational symmetry. Okay, the last one, does this parallelogram have rotational symmetry? Well, the answer is yeah. And if it's rotated, or I should say twice during a 360-degree rotation, it's as it looks right now. And the magnitude is 360 divided by that 2, which is 180. So a half turn puts the image like it looks right now, and then another half turn puts it right back to where it started. So it has an order of 2. So that's the idea of symmetry, and that's the idea of magnitude and order, and line symmetry that we hit earlier. There's some other ideas you'll see tonight, but nothing that you haven't done before. Just make sure that you look through the examples if you have questions, or obviously the Alex program is going to give you more information if you need it. So make sure you use that, and let's make sure we get the homework done tonight. All right, I'll talk to you later.